Today we will cover 9.2, 9.3, arithmetic sequence and series. In 9.2, 9.3 we have geometric sequence and series. So we had been dealing with the general setting for sequences and series last time in 9.1. Today we will cover two special sequence and series. The first one is arithmetic sequence, which is defined to be a sequence that has a common difference. That common difference usually denoted by this D here. In our first example in 9.1, our meeting last time, we have this example for the sequence 5, 8, 11, and 14, in which that from one term to the next term, so if you pick any two consecutive terms, the difference is the same. Okay, now this difference D usually defined to be the current term or the next term minus the current term. Okay, now in this case, the next term minus the current term is 3. Now in this section, we will focus especially on these three big questions. Suppose we are given a sequence. How do we know that it is arithmetic? Which is easy. You just see, pick any two consecutive terms and see if they have a common difference. Okay, and then second, suppose we are given two terms of an arithmetic sequence. Can we find the general term? And last one is the arithmetic series and the summation notation. Okay, let's say, for example, the one we have earlier. In that example 1, we have 5, 8, 11, 14, and on. Notice that the first term is 5, and then the common difference is 3. Now, make sure when you see the common difference, don't check only one pair. Try to check some more random pairs, okay, and see if the sum is consistently 3. I mean, the difference is consistently 3. Okay, so I did here 8 minus 5, that's equals to 3. 11 minus 8, that's equals to 3. 14 minus 11, also equals to 3. Then we are sure that this is arithmetic because they have common difference. Now, we will develop the general term formula. Now, instead of going to the formula, let's do the example. Let's see from this example first. Notice that the first term is 5. The next term, I will add 3. Right, so the second term is 5 plus 3. The third term, I add 3 again. I add 3 again. So the second term, right, plus another 3. The fourth term, I add another common difference. So whatever I had before, I add another common difference. Right? Now, I hope then you see the pattern that we always have the first term. We always have the first term, and the number of differences we add is 1 less than the n. So let's say here the n equals to 2. We add only 1 times 3. When the n equals to 3 here, right, then we add twice 3. When n equals to 4, we add 3 times 3. So I hope from here we can see the pattern that the nth term of an arithmetic sequence is given by, in this case, 5 times 5 plus 1 less than n times 3. Okay, yeah, of course we need to simplify. So in this case, I get 5 plus 3n minus 3, which is 3n plus 2. So suppose somebody asks, okay, what is the 100th term? And then the 100th term will be 3 times 100 plus 2. That's 300. Okay. In general, the nth term of an arithmetic sequence is a sub 1, the first term, plus 1 less than the term times d. That's in general. Now, suppose I pick question from the book. Suppose, for example, let me pick question number 10. Question number 10, 4.2, 1.5, negative 1.2, negative 3.9, and on. Now, this section is on the topic for this section is arithmetic. So we know this will be arithmetic at least, right? But in your test, you don't know if that will be arithmetic or not. So make sure you do this kind of test. Okay. So A2 minus A1, that's 1.5 minus 4.2. I think that's negative 2.7. Now do likewise for the next consecutive terms, like negative 1.2 minus 1.5. Are they the same? In this case, they're the same. Just to check. You don't want to think that it is arithmetic while it turns out it is not arithmetic. Right? Negative 1.2. You will see this is also 2.7. So from here, we see that the first term is 4.2, and the common difference is negative 2.7. Okay, now then from there, maybe I say that first. So from here, we confirm that it is arithmetic. And the first term is 4.2, and common difference is negative 2.7. So the general term a sub n will be 4.2 times, plus n minus 1 times d, negative 2.7. Okay, so my a, the first term is a sub 1, my d is, in this case, negative 2.7. Of course, simplify whenever possible. So that's 4.2 minus 2.7n plus 2.7. I get 6.9 minus 2.7n. Okay, now some little notes. Make it small enough so that you know it's little notes. Arithmetic sequence, even though this is a little note, it's quite useful. When it comes to arithmetic sequence, the general term similar to linear function. Linear function y equals to mx plus b. Now I say it's similar, not the same. Okay, not the same, similar. I say it's similar. So one way to identify one way to identify if a general term is coming from arithmetic sequence is to see if the general term looks like a linear function. You see, like if we look back here, it is as if we say that this is the slope, negative 2.7, and this is the y-intercept, right? So you can see this as y equals to negative 2.7x plus 6.9, like that, okay? So if it mimics linear function, similar structure to linear functions, then that sequence is arithmetic sequence, okay? Now, I hope that little note is helpful. I'm not saying that they're exactly the same, no, but it has the same pattern, which is something times n plus a constant, okay? Now, that will be very useful later on, though. That will be very useful later on when we deal with summation notation. Let's see another example. Suppose I do example number 16. 16 in our textbook at 9.2. It gives here the fourth term is 14. The 11th term is 35. The question is find the common difference. And I will do follow-up, find the first term, and therefore later on we are able to find the general term, okay? Even though what they ask here, only the common difference. Now, how do we solve this? I will rewrite it this way. We know that the fourth term is the first term plus how many difference? How many d's? 1 less than, right? That will be 3d, is that right? Okay, and 11th term will be the first term plus 10 times b. Right? I take it from here. That's what I did. I basically plug in n equals to 4 and n equals to 11. Now then, using these two results, I plug that in. The fourth term is 14. And the 11th term is 35. Now notice that we suddenly have an equation with two equations with two variables. We can do it the other way actually, but I prefer to do it this way for now. When I subtract, I will get negative 21 equals to negative 7d. Therefore, d equals to 2. That's my common difference. Okay. Another way to look at that, you can see the following: a sub 4, a sub 5, a sub 6, all the way to a sub 11. The thing is, how many times do you jump? How many d's do you add? You add 7 d's. So we can say that the 11th term equals to the 4th term plus 7 times the difference. Okay, that's just another way though. So 35 equals to 14 plus 7d. Fast forward, d equals 3. Okay. So you can use this method too. Okay, I still prefer this one, even though it's longer. It has better structure. Now then, that's the common difference 3. Okay, then how do I find the first term? Then you plug in into either one of these equations here, either equation 1 or equation 2. Let me put it in equation 1. So the fourth term, which is 14, equals to a sub 1 plus 3 times common difference 3, which is 9. So the first term is equals to 5. Okay, now then the general term, the nth term, will be 5 plus n minus 1 times 3. which is 3 and plus 2. Okay, that's the general term. Now, let me ask you to try number, see which question is good. Number 24, maybe? Number 24. Number 24, the ninth term is negative 253, and the 412th term is 2,971. The question is actually asking you to find the 500th term. Find the 500th term. But let's do it conventional way first. Then I teach you this question is this type of question. Arithmetic sequence is something already done in our algebra 2 actually. Okay, so the way I show you in black color right now is basically an algebra 2 method to do it. Okay, and the red color that I did earlier like this, you can say this is the Precalculus way. But there's actually not big difference in between how to solve these two though. Okay, one of them slightly faster because we do a little shortcut. Okay, but in general, that's not the case. To find this, need to find the 500th term. It's advisable for us to find the common difference. First, that's the first thing you will look for. And then after that, I get the first term. And then after that, I get the general term. And then after that, I get the 500th term. So we basically look for the function first. Okay, so that's the first method. Okay, do you want to do it yourself or do you want us to do together? Let me give you maybe 1 or 2 minutes to have a feel on this question. Okay? Together. So we have the 412. I'll write the 412 first. Okay, 412 term is the first term plus 411D, while the ninth term is the first term plus 8D. And then I substitute 2,971 equals to the first term plus 411D, and then the ninth term is negative 253 equals to the first term plus 8D, such that when I subtract, I get this is 4, this is 12, this is 12, this is 3. When I subtract this, I get 403D. Ooh, that seems to be ugly. Why do we try? So my D will be 3,200.4 over 403. I'm not sure. I don't think this is. So okay, this is 8. I was so scared. Some numbers just so ugly to the max. Until, and it takes me some time to stare at that number and then realize, oh, that's actually a nice number. The D is 8. Okay, now then maybe I use A sub 9. So I plug that into A sub 9 equals to the first term plus 8D, right? So negative 253 equals to the first term plus 8 times 8, which is 64. So our first term will be negative 317. Now, consequently, Then the general term will be the first term, negative 317 plus n minus 1 times 8, which is negative 325 plus 8n. Go on further, then the 500 term will be negative 325 plus 8 times 500, 4,000. That would be 3,675. Okay, now let me offer you another method, slightly more advanced, but this second method basically not requiring us to find the first term, not requiring us to find the general term. So what we know is the 412th term, equals to the 9th term plus how many times the difference. Basically, how many times do we need to jump from the 9th term to 412th term? How many times do we need to jump? That's 412 minus 9. That's 403 times. Okay, so I basically get this. That's 403 times d. Now, I know both the 412 and the 412 term and the 9th term. 412 term, what's that again? 2,971 equals to negative 253 plus 403d. Fast forward, you will get the d equals to 8. Now then, going further, the 500 term equals to 412 terms plus how many times do we need to jump? 88d, correct? And that's 500 minus 412, that's 88. That's how I get that 88. And this is 2,971 plus 88 times 8. 64 times 11, 704. So I get 3,675. Okay. So the second method basically didn't need to look for the first term, didn't need to look for the nth term, okay, the general term, but just go ahead with the 500 term. Okay. Now let me go on. The last part of this section, which is still, even though that's the last part, it's still a big portion, the arithmetic series. Arithmetic series is a series that whose terms form arithmetic sequence. Okay, now with that said, then you will see if we write that in summation notation, then the terms that we are adding there will have an arithmetic sequence general form. Okay, the terms here has is the general form, general term of an arithmetic sequence. So for example, the following. For example, if we have the sum k equals to 1 to 10 of 3n plus 2. Now notice that the terms here follow very similar to linear function. So this must be arithmetic series because the terms follows arithmetic sequence. Okay. Now, how about the formula? Oops. Sn. This Sn is actually a common notation for summation, but specifically once we use subscript n, it refers to the nth partial sum. Which means we are adding the first term all the way to the nth term. Okay, or in our summation notation, there will be the sum from the first term to the nth term of the sequence. Okay, now what is the nth partial sum for arithmetic sequence? Arithmetic series. For arithmetic series, the nth partial sums will be given by n over 2, the first term plus the last term. Okay, that's the formula. That's the formula. Now we will next apply this formula. We'll next apply this formula, and then I will explain to you why the formula looks like that. Okay, let's say for example, I want to add this 5, 8, 11, 14, all the way to, let's see, 3, all the way to 26, let's say. Okay, and we see the first term is 5. The last term is 26. Now, what's the number of terms? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 terms there. Okay, so according to our formula, the 8th partial sum of this sequence, so this forms arithmetic series, is there are 8 terms there divided by 2. The first term 5 plus the last term 26. So that would be 4 times 31, which is 124. Now, of course, we are not. I'm not anticipating. You should not anticipating answering questions like exactly like this in your test, because to add 8 terms, all you need to do is just use your calculator and add them, right? Now, the thing is, what happens if we have 40 terms or 400 terms? I don't think you want to add them one by one, and you will prefer to use formulas, right? Okay. Now, but let's see. Using this example here, why the formula looks like this. Okay. Now I'm not going into technical proof of that formula. I can. In fact, if you look at my precalculus lecture at Wesleyan College, you see that I actually show them the technical proof of that formula. But for you, if you are interested to find the technical formula, then see that lecture video yourself. Okay, the first term is 5, the 8th term is 6. But the key of the proof is actually from the following observation. Notice that the first term plus the last term when we add the first term and the last term, is the same sum to if we add the second term with the second from the last. Okay? The sum is also 31. So the first with the last, second from with the second from the last, the third with the third from the last, and so on. The sum will be the same. So the total will be, the total basically will be the number of pairs times the total, I'm sorry, the sum of each pair. Which is each pair has the same sum, right? Okay, now the number of pairs is easy. Each pair takes two terms, right? So the number of pairs will be the number of terms divided by 2. Okay, the number of terms divided by 2. And then the sum for each pair, because each pair has the same sum, all I need to do is to get the first term and the last term added together. Okay, that's why we come up with that formula. Now, the formal proof of that, of course, takes longer time to prove, right? That's why I don't go into that. Okay, that's the formula. Now, then we are ready to do problems. Okay, for example, if I do number 30, we are given that the 6 terms, not the first term, the 6th term is -2, the common difference is -3, 4, and we need the first 40 terms. Yeah, because the question is find S40. Now, I feel strange. Our textbook use capital S, is supposed to be lowercase s, okay, for the nth partial sum. Yeah, for the nth partial sum, supposed to be lowercase s, not capital S. Well, anyway, don't worry about that. Notice that S40 means I need to find, the formula is 40 terms divided by 2, that's the number of pairs. And then I need the first term, which I don't have yet, but I can find it, and the 40th term. Is that right? Now, how do I get that? Well, notice that I have the 6 terms and the D that will be enough for us to find the first term. Okay, so the 6th term is -2, the first term is unknown, the D is -3, 4. So -8/4, I do LCD right away. First term minus 15/4. So the first term is 7/4. Now how about the 40th term? 40th term will be the first term plus 39 times the common difference. That will be 7/4 minus 117/4. That is -110/4, which is -55/, you know what, let me just divide it right away. 55/2 is 27.5. -27.5. Then, going back to the formula, so I have all the ingredients for that 40th partial sum. So, the 40th partial sum of an arithmetic sequence is 40/2, that's 20. The first term is 7/4, and the last term is negative 27.5. So that's 20 times, this is 1.75 minus 27.5. Then you can use your calculator. 1.75 minus 27.5 multiply point. I get negative 515. Okay. Now, what if the summation notation, the arithmetic sequence or the arithmetic series given to us is in summation notation? Let's say, for example, number 34. Number 34. We add k equals to 1 up to 10 of 1 for k plus 3. Notice that this looks like a linear function, right? Just make sure, you need to make sure that the indexing k is the k that you have here. Okay, make sure it match. Now then, from here we see, oh, that's an arithmetic series. The first term is 3.25. The last term, that's 5.5. So that series is the first 10 terms of arithmetic sequence. That is 10 over 2, the first term 3.25 plus 5. Okay, so that is 5 times 8.75. I think it's 55. 8.75 times 5. See? No, it's not 55. I get 43.75 instead. In my old test, I think, or my old quiz, I think I once asked this type of question. For example, but you need to think a bit more. What if the k is not starting from 1? Let's say I start from 7 and up to, let's say, 100. And here I have 1 4 k plus 3. There are actually more than one ways to do this. There are actually more than one ways to do this. But the way I see is seeing it this way. The way I think is appropriate. I will see what is the first term first, but in this case, the first term is the 7th for the k, when k equals to 7. I get 7 over 4 plus 3. That's 4.75. And the last term in this case, the 100, a sub 100, that's 1 4 times 100 plus 3, that's 28. Okay, now notice that this is still arithmetic though. This is still arithmetic. Okay, so the sum will be, the sum here will be how many terms? 100 minus 7 plus 1, don't forget that, okay, over 2. That's the number of terms. This is number of terms. Okay, and then the first term is 4.75, the last term is 28. So 100 minus 7, 93 plus 1, 94, divided by 2, 47. So this is 47 times 32.75. Okay, so the series is still arithmetic series, even though you don't start from k equals to 1. Okay, so when I write it down, it's actually, if I write this series down here, you will see that it's actually, when k equals to 7, 1.7. So it's 4.75 plus 5 plus 5.25. You keep on adding 1/4, right? All the way to 28. But this itself actually form an arithmetic series, right? It actually forms an arithmetic series whose first term is 4.75. I don't want to use a sub 1 anymore because a sub 1 is not, I don't want you to confuse that with this. Maybe I call that b then instead. Okay, let me call that b. So b1 now is this, okay, and b47 is 28. Yeah, b47. No, that's not b47. B94, not 47. Okay. B94. Yeah, 94 terms there. Okay, so and this will be 94 over 2, the first term, plus the last term. Okay, now of course what you do, you still show this work, the one on in black color, but at the back of your mind you have this pattern. Okay, this is in your mind. This is what you write. Okay, now lastly, a bit heavier. Oh, actually not lastly, that's not the last one. Let me do number 44 first. Number 44, I get 2 plus 11 plus 20 all the way to 16,058. First challenge is write in summation notation. The summation notation will be, our k will be from 1, but we still don't know this yet. Okay, and then it will be a sub n here, right? Now the nth sequence, the general term, is unknown. Okay, it's unknown. But what is the first term? The first term is 2. The common difference is, I think the common difference is 9, right? So I can find the general term with this. This is 9n minus 7. Okay, so with this, then I can update my summation notation. This will be 9n minus 7, but I still don't know how many terms there. I still don't know how many terms there. Well, Let's do this then. I know the final answer. The last one is 16,058. 9n minus 7. So for n here, 16,065 equals to 9n. So divide by 9, 16,065 divided by 9, I get n equals to 1785. Okay, so the summation notation now being updated becomes from 1 to 1785 of 9n minus 7. That's the summation notation. Okay, so I get the general term first. Using this known, I get the general term, and then use that general term to see how many terms there. Then we get our, maybe I pick and put it here. Okay, those are the steps. Then, next, let's find the actual sum. Let's find the actual sum. So the 1,785th partial sum will be 1785 over 2 times the first term 2 plus the last term 16,058. Yeah, anything from here is calculated. 16,060. I have my calculator, let me just use it. 8,030 times 1785. I get 14333,550. Next one, before I go to something not really related to arithmetic, but it does. Number 50. Find the number of terms with in the arithmetic sequence. So we know it is arithmetic. We know it's arithmetic. But what we know from that arithmetic sequence are only the following. We know that the sixth term is -3. The common difference is 0.2. And s equals to -33. That's all we know. Okay, so s sub n is -33. The question is how many terms are there? Okay, how many terms such that the sum of that nth term is -33. Okay, let's do that. Let's find the first term first. I think we can get it from here, right? So the 6 terms equals to the first term plus 5 times d. So -3 equals to the first term plus 5 times 0.2, which is 1. So the first term is -4. The general term, therefore, the nth term, therefore, will be -4 plus n minus 1 times d 0.2. Okay, so the sum, the nth partial sum of this arithmetic sequence is n over 2 times the first term -4 plus the last term 0.2 n minus 4.2. Let me substitute that S sub n. S sub n is known to be -33. This is n over 2, 0.2 n minus 8.2. Oh, let me divide by 2 to make my life easier. So n times 0.1 n minus 4.1. Okay, so actually now you see it forms a quadratic equation. I just multiply them first instead of dividing by 2. This is 1/2 times 0.2 n squared minus 8.2 n. Hope it's better now. And then I need to solve this. You know what? Let me multiply by 10. So I get 0 equals to n minus 33. Oh, is it 33 or 30? 30 times 11. N minus 6. So either n equals to 30 or n equals to 11. There are two possibilities. There are 30 terms there, or there are 11 terms there. Okay. Now suggested homework from here. Suggested homework from here. I don't want you to do a lot such that you don't have enough time for your test 4. Just do some, okay? Just do some. Let's say from number 3, I suggest you to do from number 3 to number 49, but just do every other odd. Okay, don't do too much. Get used to the manipulation of the formulas. Get used to how to manipulate the formulas. Okay, so if we have arithmetic sequence, okay, then the n term is the first term plus n minus 1d. And then the nth partial sum will be n over 2, the first term plus the last term. Now, of course, speaking about variation, there are a lot more variations from here. But whatever variation you deal with, if you try to create shortcuts, you may have a lot of shortcuts and get confused which shortcut to use. That's why I don't really want you to think about the shortcut. Think about how to apply these formulas. That's better. Okay. Instead of thinking of so many different ways to do so many different questions, you better know how to manipulate these two formulas to do so many different problems. Okay, now that's for 9.2, arithmetic sequence and series. The last section for our semester is 9.3. That is geometric sequence and series. Now, definition. A sequence is geometric and therefore we call it geometric sequence. Sometimes we also call that the geometric progression. Okay, maybe I'll write it down. It's geometric also known as geometry sequence or geometric progression. For your level, we will just call it geometric sequence. But once you go a bit further, then you start seeing some professor actually call that geometric progression. But it's just a word play. Don't worry about that. Now, a sequence is geometry if the ratio, not difference, if the ratio of any consecutive terms, any two consecutive terms, is a common ratio R. For example, if we have, let's say, 1/3, 1, 3, 9, 27, and on. You see, I keep on multiplying by 3, right? I keep on multiplying by 3. Multiply by 3, multiply by 3, multiply by 3. Instead of adding or subtracting by common difference, we multiply by common ratio. Or we may also have, let's say, 4 and then 4/5, and then 4/25, 4/125, and on. Here, the common ratio is 1/5. I keep on multiplying by 1/5. Multiply by 1/5, and on. Okay. Now, for us to see what is the general formula for the general term, let's use this example 1, the first example in this example 1. So the first term is 1/3, right? The second term is multiplied by 3, right? Multiplied by 3. The third term will multiply by another 3. The fourth term will multiply by another 3. Notice that then we see they have the following general pattern. The nth term is the first term times the common ratio to the 1 less than n. Right? The nth term in this specific example here, the nth term will be 1/3 times 3 to the n minus 1. Okay, we can apply the same idea here. You see that the first term is 4, the second term is 4 times 1/5, the third term is 4 times 1/5 square, right? And if you go on further, then you will see the nth term is 4 times 1/5 to the n minus 1. Okay, now you see consistently, if we have geometric sequence, it must follow this common term formula. Okay. Then how do we use this? How do we use these formulas? Suppose we are given the following. We have geometric sequence. Where the third term is 5 and the sixth term is negative 40. The question is, let me do it a long way first. The question, find the common ratio first, and then find the first term, and therefore we can find the general term, and specifically the 10th term, let's say. Okay. Just like in our arithmetic sequence, I will show you two different ways. The one in black will be the standard way. That's a long way, okay, but with better understanding. And then the one in red later on will be the one more into your intuition. Okay, now using formulas, the third term is the first term times r squared, while the sixth term is the first term times r to the fifth. Notice that the exponent here is always less than the n, right? Okay, just like before in our arithmetic sequence, okay, the number of d's will be one less than the n. Now, I plug in numbers. So I get 5 equals to the first term times r squared. Negative 40 is the first term times r to the fifth. Now, you can do substitution if you want, right? If I use substitution, then you see that negative 40 equals to the first term times r squared times r cubed, right? Notice that if I add these, I get that r to the fifth, right? And then you substitute that this guy here to be 5, right? So negative 8 equals to r cubed, r equals to negative 2. Is that right? Okay, now that's one way to see that. But let me offer you another way. I don't think we see this anywhere in our past lesson, even in your previous classes. Notice that if they actually differ by some constant, not differ, it has a ratio, okay? Now then what you can do is you actually divide 5 over negative 40 on the left hand side equals to a sub 1 r squared over a sub 1 r to the fifth. You can do that also. So you can use the red color, the blue color I show you on the right hand side. You can also show what I did just now. Okay, so I get negative 1a equals to 1 over r cubed. So r cubed equals to negative 8, r equals to negative 2. Okay, so you can use either one of them. But if you can actually feel it intuition-wise, then actually you will see that the sixth term equals to the third term jump 3 times. Right? You jump 3 times. So a cube, I'm sorry, the third term, the fourth term, the fifth term, the sixth term, you need to multiply by r, by another r, by another r. Does it make sense? Okay, that's just an intuitive way to look at that. So that's how we can come up with these formulas here. Okay, but if I show my work as a teacher, then I will show my work to you using this black color. Okay, now then, once I get the r, which is negative 2, then I can proceed finding the first term. Let me use the third term equals to the first term times r squared. The third term is 5. The first term is unknown. The r is negative 2 being squared. So the first term will be 5 over 4. So our general term, a sub n, maybe I go on a sub n. Therefore, the general term will be the first term 5 over 4 times negative 2 to the n minus 1. Okay, using that, I can find the 10th term. 5 over 4 times negative 2 to the 9. And it's negative 5 over 4 times 512. That's negative 128 times 5. 6040. Or 640. Okay, I'm about to give myself a break, and of course, together with you, I would like you to try question number 8. Number 8, the sequence is to 6, 18, 54, and on. Find the n term. I think that one is easy. Just find the n term. Okay, now use the same idea for number 12. It may confuse you a bit, but it's don't worry. You just have extra x here. So your answer later on will include x. And then number 26. So find a sub n, the general term, if the second term is 3 and the fourth term is 6. Okay. Now, each question, I think 1, 2, 3. So 6 minutes plus 10 minutes break. We come back at 11 o'clock. Okay, I already started number 8 and number 12 has these solutions. When I underline this way, it means you can choose either one of the solution. So you can use this, but our textbook may show this one instead. Okay, you can use this, but our textbook may show this one instead. In other words, it is possible that our textbook wants you to simplify a bit further. Okay. Now, uh, if I were you, simplify as much as possible. Now, like this negative here, the negative that you see here, it's actually a common practice that we separate that negative. Yeah. Remember the alternating sequence? So if it is an alternating sequence, you try to separate the negative one to some power separately. Okay. Now then number 26, the second term is 3. The fourth term is the second term times r squared. It jumps twice, right? Okay, so you will see 6 equals to 3 times r squared equals to 2, r equals to square root of 2. Or you may use another method to do that, okay? And then the first term, therefore, is, the second term equals to the first term times r. 3 equals to, actually I'm missing something. I should use plus minus here. Okay, so for r1 equals to radical 2, then 3 equals to a sub 1 times radical 2. The first term is 3 over radical 2. Or 3 radical 2 over 2. Now, however, if we pick the negative branch for that r, which is negative radical 2, you will see that the first term is indeed negative 3 radical 2 over 2. Such that the general term a sub n, in this case, that will be the first term 3 radical 2 over 2 times radical 2 to the n minus 1. Which we can actually simplify a bit further. Notice that this is, if I multiply this radical 2 in there, it will give me 3 over 2 square root of 2 to the power of n. Okay, if we simplify that further, and if you want to simplify that even further, this is actually 3 times square root of 2 to the power of n minus 2. Now the reason is because you can rewrite that 2 as square root of 2 being squared, right? Okay. Now, if the r is negative 2, then the nth term will be negative of 3 radical 2 over 2 times negative 2 to the power of, negative radical 2 to the power of n minus 1. I bring this negative 1 to the power of 1. I try to simplify. And together with the negative there, I get negative 1 to the power of n minus 1, right? And I have 3 radical 2 over 2 radical 2 to the power of n minus 1. So this will give me negative 1 to the n times 3 over 2 times square root of 2 to the power of n. Now the alternator usually written first. So 3 times square root of 2 to the power of n minus 2, if you like. So you can be you can say this is the answer, or our textbook or other textbook may write this as the answer. Okay, it's just a common practice. If it is alternating, we separate the -1 factor, -1 to the n. Okay, and we try as much as possible to absorb the tool, radical tool, or tool into the formula. Okay. Little notes that I write there, I think that's quite useful, is that the general term of geometric sequence has similar pattern to exponential function. Okay, now this is in particular very useful if we are given a geometric, let's say a geometric series. Okay, a geometric series is the series whose term follows geometric sequence. Okay, so we know that, for example, the summation is something looks like this. Like that. Okay, or basically you will see the summation of any number, whatever that is, times r to some power n. Then you see that this is actually similar to a times b to the x. It follows very similar to exponential function. Okay, actually, how to move from here to here. How to move from here to here. This is a sub 1 times r to the n over r. Now get this together, make it rb. Okay, so suppose, for example, the following is geometric series. The summation k equals to 1 up to 10, let's say, of 2 times 3 to the k. That's a geometric series. Why? Because it follows the terms here look very similar to exponential function. Okay, in fact, we will see that the first term is 2 times 3 to the 1, that's 6. And the ratio is 3. Okay. Now, formula for geometric series. The sum of the first n terms, the n partial sum of a geometric series, is given by the first term times 1 minus r to the n over 1 minus r. And if the magnitude of r is less than 1, S, which is the infinite sum, infinite series, so you add up to infinity, is given by the first term over 1 minus r. let me do one example first. If you want to see the technical proof for that, again, you go back to my Precalculus lecture. But I give you examples here better. Suppose I have this 3 and then 6, I multiply by 2, multiply by 2, multiply by 2, multiply by 2. And then I want to find as, let's say, 10, which is the sum of the first 10 terms. Okay, the sum of the first 10 terms. Okay, equals to 1 to 10. Now then, what is the general terms here? The first term is 3. The common ratio is 2 to the power of k minus 1. Right? So this is the notation for the 10th partial sum. This is the summation notation for geometric series. Okay, now what's the formula? Apply the formula. So the first term is 3 times 1 minus the ratio to the 10, there are 10 terms there, over 1 minus the common ratio. So this is 3 times negative 1023 over negative 1. That's positive 3069. Okay. Or another example, let's say I have 3, instead I will divide by 2. I will divide by 2 instead. And I want to find out what is the sum of the first 10 terms. You see, I start from 3, that's the first term. The common ratio is 1/2. That will be 3 times 1 minus 1/2 to the 10th over 1 minus 1/2. It will be 3 times, at the bottom that's 1/2. On the top this is 1 minus 1 over 1024. Multiplied by 2 on the top, and at the bottom that will be, multiply the top and the 4047, I'm sorry, 2047 over 2047 over 1024. That will be 6141 over 1024. Or you can also use your calculator if you like. Now, in this case, because the ratio, since the ratio is 1/2, which is less than 1, then the sum will not go to infinity. The total sum, the infinite sum, will not go to infinity. That will be equals to the first term, which is 3, times 1 over 1 minus half. to C, that's eventually 6. Okay. Now, why the formula becomes like that? If you see the S infinity, it's supposed to be 1, the first term, 1 minus R to the n over 1 minus R, right? Now, if R is, let me use this example. So, if R is less than 1, the magnitude is less than 1, this becomes go to infinity, right? This goes to infinity. Now, 1/2 to the infinity, 1/2 to the infinity will be 0. How do we know, Thomas? 1/2 to the infinity goes to equals to 0. Well, because of exponential function. If you remember exponential function, b to the x, right, will go to 0 as x goes to infinity when the base is should be positive base, right? Is less than 1. The graph looks like this. The graph looks like this. I hope you remember that. And the y-intercept is 1, right? But because the b is less than 1, then when x goes to infinity, it will be approaching 0. Now, that's the quantity that I use here. Okay, so that's why the formula basically on the top becomes 1 minus 0, okay, or simply just 1. Now, even though I don't give you the technical proof, I will show you how things actually work. Suppose for our S10, for this 3 plus 6 plus 12 plus 24 and on, up to the 10th term. Up to the 10th term. I don't know what's the 10th term. Okay. Now, let me show you how it works. And this try to apply when you watch my lecture video at West LA College one. Try to imagine this example here and apply that to the technical proof. Notice that the ratio is 2, right? So what I plan to do is I multiply multiply this equation here by 2. That's the ratio, right? By 2. Okay, so if I multiply by 2, the whole thing to the sum here, then the 3 becomes, this 3 becomes 6. The 6 becomes 12. So on and so forth. Okay, the last term we have here, even though I don't know the number, I know what it should look like in terms of the pattern. It will be 2 to the 9. Right? So when I multiply by 2, multiply by 2, multiply by 2, the last term, when I multiply by 2, that will be 3 times 2 to the 10. Then what I will do next is I subtract. Then I will get as 10 minus 2 as 10, and y2, the ratio. Okay, y2 here, that's because that's the ratio. Now then on the right hand side, when I subtract, I will get 3, which is the first term, minus 3 times 2 to the 10. Now factor this 10th partial sum. Equals to 3, factor 3, 1 minus 2 to the 10. Yeah, I use rectangular this 10 comes from the 10th partial sum, while this 2 comes from the ratio. Then as 10, the 10th partial sum will be the first term times 1 minus 2 to the 10 over 1 minus 2. That's why the formula looks like that. Now we are ready to do problems. Let me pick question number 30. Question number 30. The fourth term is 4 over 13. The common ratio is 1/4. And I need to find S6. Again, this is geometric sequence. Now, what I will do, I will find the first term first. Okay, so the fourth term, is the first term times r cubed. Is that right? So 4 over 13 equals to the first term times 1/4 cubed. So the first term is 4 to the 4 over 13. Let me just leave it like that. So what is S6? The sum of the first 6 terms. That will be the first term times 1 minus the common ratio to the 6, the number of terms, over 1 minus the common ratio. Oops, this is one. Okay, so I get 4 to the 4 over 13 times 1 minus 1 over 4 to the 6 over 1 minus 1/4. Let me cut to the chase. I will multiply the top and the bottom by, you know what? No. I will distribute the 4 to the 4th. Let me distribute this. I hope that way the number's not growing up too fast. So I get 4 to the 4th minus 4 squared over 13 times 1 minus 1/4. Yeah. Let me multiply by 1/4 again. I will multiply by 4 again. Then I will get 4 to the 5th minus 4 cubed over 13 times 4 minus 1. Yeah. Then from here you use your calculator. I can factor 4 cubed, 4 squared minus 1 over 3 times 10. So 64 times 15. 960 over 3 times 13. I can reduce by 3. 320 over 13. My answer is different from the book. Do I make mistake? Here. It should be 4 to the negative 2 here. My bad. Oh, once I make that mistake, it's troublesome. I need to erase this. My bad. Sorry. That one little negative screwed me up. So I'll multiply by 4 squared over 4 squared. That will give me 4 to the 6 minus 1 over 13 times 16 minus 4. So 4 to the 6 minus 1. 4095 over 13 times 12. I think I can reduce by 3. If I reduce by 3, we reduce by 3, I get 1365 over 13 times 4. Oh, but 1365 is multiple of 13. Okay, well, then this is 105. Number 32. I'm done with the material. What I do now is just working on problems, applying those three formulas. So when k equals to 1 up to 9, that's number 32, of negative radical 5 to the k. So the first term when k equals to 1 is negative radical 5. The common ratio r is negative radical 5 too. So the sum, that's the sum up to 9, right? From the first term to the ninth term. That will be the first term times 1 minus negative radical 5 to the ninth term over 1 minus the ratio. Okay, now then from here, I guess we will just use calculator. No, I don't want to use calculator. Hold on, I don't want to use calculator. Let's see what I can do here. Multiply by the conjugate. Multiply by 1 minus radical 5. 1 minus radical 5. So I get at the bottom 1 minus 5. And on the top I get negative radical 5 times 1 minus radical 5 times 1 plus radical 5 to the north. So I get negative 4 at the bottom, cancel with the negative on the top, I get 1/4 radical 5, 1 minus radical 5. This is 1 plus 5 to the 4th, 625 radical 5. Now just keep on multiplying that then. This is 1 plus 624 radical 5 minus 625 times 3,100. 624 radical 5 minus 3,124. So 624 divided by 4 times 5. That's 780 minus 3,124 divided by 4. Let's multiply 4. 780. Number 40. Have 3 plus 3 fifths plus 3 over 25 all the way to 3 over 625. Yeah, oh, okay, I'm just missing one term. So the first term is 3. The common ratio is 1/5. I hope you agree with that. So the general term will be 3 times 1/5 to the n minus 1. Or we can also say this is 3 times 5 to the 1 minus n. We can also do that. Okay, so the summation notation will be, they want us to write it in summation notation. So when k equals to 1 up to 5, there are 5 terms. 3 times 1/5 to the k minus 1. Or if you use this notation here, this is k equals to 1 to 5, up to 5, 3 times 5 to 1 is k. And either one is okay. Number 48. Find the sum of 250 minus 100 plus 40 minus 16 and on. The first term is easy to see, that's 250, but the ratio is not really. So let me do it slightly long way. Negative 100 over 250, that's I think negative 250. Negative 250. So the infinite sum will be the first term, 250 over 1 minus the common ratio. If I multiply the top and the bottom by the LCD 5, I get 1,250 over 5 plus 2, which is 7. And I don't think that's multiple of 7 there. Okay, now I'm basically done with this section here. But some side note, which is important, once in a while I ask this question. There's a statement that we saw long time ago in pre-algebra. I think that's at least in pre-algebra, very likely in arithmetic you saw that also. A rational number is a number. A number is called to be rational if that number can be written, a number that is written, that is rewritten as a fraction, a over b, where the denominator is not 0. I think I should say that. Can be rewritten. Can be rewritten. You basically can rewrite that as a fraction. That's why we call that rational number. Okay, we can write that as the ratio of two integers. Let me emphasize the a and b there are integers. And then at that time, they say that all integers, of course, is rational, all fraction also rational. All terminating decimal also rational. The terminating decimal. Can I scroll up a little bit? Scroll up like this. Okay. So one of the group that is considered rational numbers is terminating decimal. And this one we can, we did that even in the algebra. Let's say if I have 3.57, right? We can rewrite this as 3 plus 0.57. The 3 is already rational, right? But how about the 0.57? Well, 0.57 can be rewritten as 57 over 100. So you can write that as a decimal, right? That one is not an issue. However, it's not an issue, but the one that's still a question that at that time they did say, but we never really prove it, is the repeating decimal case. One of the well-known one is 0.333333, which we write as 0.3 bar. Okay, or we may even have two numbers repeating, 0. Let's say 19 bar. Now the thing is, in pre-algebra until algebra 1, we only took this as a fact that it is we can rewrite it as a rational number, but we never really find what's the rational number that gives us this repeating decimal. Okay. Now, if you got into a good algebra 2 class, a good intermediate algebra class, then your teacher is supposed to mention this a bit. Okay. But by the time you pass Precalculus, you're supposed to know how to rewrite this, how to find the rational number that gives us this repeating decimal. Okay, now I will do it with a textbook way first, 0.3 bar. Notice that I can rewrite this as 0.3 plus 0.03 plus 0.003 and on. Right? Now, notice that this actually forms a geometric series where the first term is 0.3, right? And then I keep on multiplying by 0.1. Now, this 0.1 that I multiply by is actually coming from one digit that is being repeated. Okay? Now, if I compare with the other one, 0.19 bar, this is 0.19 plus 0.0019 plus 0.000019 and on, where the first term is 0.19 and the common ratio is 0.01. 0.01 is because I'm repeating two numbers. Okay, not only the 1, not only the 9, but 19, 19, 19, 19. So then this 0.3 now, 0.3 bar now can be seen as the first term 0.3 times 1 over 1 minus 0.1. that is 0.3 over 0.9. That's 3 over 9. That's 1. So you can use your calculator and then type in 1/3, 1 over 3. What's the decimal? You will see 0.3333333. Now, how about 0.19191919119? What does that look like if we rewrite it as a rational number? The first term is 0.1. Okay, 1 over 1 minus 0.01. That will give us 0.19 over 0.19. I don't think you can simplify that further than just move the decimal point twice to the right. Okay, if you can reduce that, then you should reduce that. Okay, but that's the basic idea. Okay, now our textbook, let's see, suppose I do number 56. So I do number 56, I get 3.2 and then 394 bar. This can be seen as 3.2 plus 0.0394 bar. 3.2 plus 0.0394 plus 0.000394 plus 0.00000. So you see, this 0 here is for this place. This 394 for this 394. Okay, so the next three numbers will be 394. I hope you see that how I push that 394 further and further down. Okay. But this guy here forms a geometric series. So the first term is 0.034 and the common ratio is 0.001. Now you see that this 0.001, you can see from I multiply by 0.001, 0.001, or you can also say that because there are three decimals that's repeating, then there are 0.001 there. Therefore, this is 3.2 plus 0.0394 times 1 over 0.001. Okay, fast forward, this is 3.2 plus 394 over 10. I'm sorry. It should be 1 minus. It should be 1 minus here. So it should be 999. Four, like this instead. Well, the sum of two fractions must be a fraction. Okay, so up to here, we also already know that it must be a fraction. Just do you know how to add these fractions? So this I multiply by 999 here to make it common denominator 990. Okay, my calculator 32 times 999 plus 394. I get this is 32362 over 9,990. I think they are both multiple of 2. So 16181 over 9,990 divided by 4,995. That's the fraction. Okay, now this is the textbook way of doing that. Textbook way to see this as a geometric series, but it's actually not necessary. Alternative method, 0.3 bar is 0.33333 on. Now let me call this guy x. Notice that it repeats every digit, every decimal, right? So if I multiply by 10, then the decimal point will actually move one place to the right. Or I basically get this. Instead of moving the decimal point, I move the 3. This guy move here, this guy move here, this guy move on. Right? Now, then when I subtract, the purpose is I move the decimals to the point, the number of times such that the repeating decimals actually coincide with the previous repeating decimal. So in this case, it repeats only one time every decimals, right? So I just multiplied by 10, and you see that this 3 here, when you multiply by 10, it goes here. This 3 here, when you multiply by 10, it goes here. This 3 here, multiplied by 10, it goes here. Right? Do you see that? Okay. Now, when I subtract, I get this repeating decimal cancel each other. I get -3 equals to -9x. So x equals to 3 over 9, which is 1/3. Bang, you're done. 0.19 bar is 0.191919 on. If I call this x, what should I multiply this by so that the repeating decimals coincide with the previous repeating decimal? I will multiply by 100. Basically, I move the numbers twice to the left. That's moving the decimal twice to the right. Okay, so I will get 19.1919. Right. This yellow here, if I multiply by 100, comes here. This blue here, multiply by 100, comes here. It's 19 here, multiplied by 100 moves here. Then when I subtract, I get -19 equals to -9x. So x equals to 19. So how about that last question, number 56, Thomas? Well, okay, let's see. Number 56, 3.2394 bar. If I call that x, notice that it repeats every 3 numbers, right? Now let me multiply by 1,000. Okay, let me multiply by 1,000. Now, if I multiply by 1,000, then this 394 will move here. 394 will move here with 32 in front of it. And after that 394, you have a bunch of 394 further. And they are repeating. Now I subtract this. I get 999x on one side. On the other side, I get 3,237.2. So 3,237.2 over 999 is our x. Move the decimal point once to the right, give me 9,990. And of course, you reduce by 2, you get 6186 over 4, 6186. No, it should be 6 here, not 7. Subtract that. Okay, now that's all I can teach during this semester. Your suggested homework from here. Suggested homework from this 9.3 will be from number 3 to number 57. Should be good enough. 3, 57. Again, just do the every other odd instead of all odd. Okay, I want you to focus on your test 4 this Monday. Okay, now somebody asked me this question earlier. Thomas, when is our test 4? Our test 4 is on June the 8th. What are the material for your test 4? 9.1 to 9.3 and then 9.5. 7 point something, 7.1, 7.2 as I remember. The whole chapter 6. And yeah, that's it. How about your final? Final is cumulative. Whatever I taught you, expect that to be there. So your final is 15. What time again? Do you remember? I think I have to say this one. Comprehensive, but what time?
I think you said it was from 8 to 11 a.m., but you were going to post it at 7:45.
That's right. Okay. So the time is different though. Okay. Different time. No. So what happened if you start at 9:30, or you think, oh, it's just regular test, so you start at 9, then you basically lose 2 hours. I'm sorry, you lose 1 hour. Okay. I wish I can change the time for your test, but I cannot. Okay, so I will post it as 7:45, and you need to turn it in by 11:15. Okay.
I'll be done on the 15th at 11:15 a.m. Come on, baby.
1:15? No, 11:15.
11:15.
11:15. Okay. Yeah. Well, anyway, sorry for the hard semester. We got into what we call new normal, but we will live through this. Okay. And I wish you all doing well, and give me an update when you get to your Calculus 1. Even if you don't make it this semester, right? If you repeat this class in the summer, let's say, for example, let me know if you the update. Okay, I know there are some material I didn't cover, which I supposed to, but I also know those materials are actually something you can study again later. Those are parametric equation, polar, polar coordinate system and polar equation. And then conic section. What else I'm missing? Oh, induction. Proof by induction. I wonder what else. Yeah, I think those are the one I'm missing. Yeah, those are the one I'm missing. Okay, you don't really need that right away from your for your calculus 1, but try to see that before you get to calculus. Okay, is there any way you can upload the solution for test 1 and test 2? I really thought I already posted the solution for test 1 and test 2. Will these topics will be on the final? The one I say here, no. The one I say here will not be in your final. But please study on your own before you get to calculus 2. Okay. Solution for test 1, test 2. I really thought that I already posted it. Let me see. Okay. Let me see. Test 1. Yeah, test 1, I already have the solution. You go to the assignment. Let me share it with you. So you go to the assignment. Yeah, you go to the assignment and then you click test 1 and you see the solution here. Okay, and then for your test 2, you see the solution here. Okay, I wonder if I post test 3 solution. Let's see, test 3 solution. Oh, test 3. Oh, yeah, I did. Yeah, test 3 solutions here. Okay. Yeah. Anything else? You're welcome.
Hey, Thomas.
Uh-huh.
Something that's helped me in the past for like the first 3 tests. I don't know if you posted or if I just found them, but I went on. I think you posted some practice exams from your website.
Uh-huh.
Are they just like the test 4 exams from your previous teachings from Precalculus?
Similar. And actually, recently I tried to make it as close. Okay, I don't expect to see even similar question in a sense. Let me show you this first. So I believe I post the test from last semester. Did I? From fall 19?
Yeah, I
Test
think you
4.
posted it for last.
Yeah, for the one from last semester, right? So
Yeah.
let me show you what I have here. I don't want to give you a misleading statement too, but for example, you do expect to see similar questions, not the same question. Okay, you expect to see similar question. This is my test 4 from 419. Okay. Now, the format, I may need to change that a little bit. The reason is because from my other classes, including your class, I have seen people write pretty big. So I have to space this even more. You see what I mean? Now for this test, I have 5 pages. But in your test later on, I think it will be 7 or 8 pages.
Just to give us more room.
Yeah, just to give you more room. So what happened was, like in my other class, my calculus 2 class, I gave them the similar test. Actually, the type of question are basically the same tests. I changed the functions, but then because I spaced it up, and I have a student actually brought it up to me. Thomas, are you crazy? all your previous test was only 7 pages, and now it becomes 14 pages.
Mhm.
And then I say that, but in my 7 pages, 1 page I have 3 questions, 2 or 3 questions, and in my format, this 14 pages, I have only 1, at most 2 questions on 1 page. So they have a very a lot more space to write on, you know. So please don't get scared. My point is, I don't want you to get scared when you suddenly see a lot more pages. No, it's the underlying concept that I asked you are actually quite similar.
Okay.
Okay. Mm-hmm.
And then my final question is for test 3. You posted the test at 9 a.m., but you were available from 8:30 to 9 for essentially like office hours for questions. Will you be available on Monday at 8:30?
I actually make myself available from 9 o'clock, from 8 o'clock that day.
Oh, okay, cool.
Yeah.
Okay.
Okay. So I try to give you basically the same amount of office hour for my test score. For the final, however, I hope I still have people here. For the final, however, I am not required to give office hour during my final week. Okay. I still don't mind to answer your questions, but please, if you have questions, ask me earlier, not on the final day. Okay. Everybody.
And ask in the email first, right?
Yes, that would be best. But on the final, especially because of the following reason, on your final is on June the 15th, right? And
Right.
you will start from 8 to 11. We have it up there. Okay. Now that day happens to be my first day of class at West LA College, which also start at 8 o'clock up to 12 o'clock. Okay. Now,
Okay.
what I don't want to happen is that you kind of rush me 7:30. Thomas, can you answer this one last question? You know, and of course I want to help you, right? But especially because it's your final, okay? Especially if I know that you are kind of like somebody who have a very good chance to get an A. I don't want because of one question you'll end up with a B. Okay, but help me to help you. Okay, if you have question last minute like this, I will try my best to help you. But then at the same time, my students at West LA College will not see me as a teacher who is on time if I do not go online with them at 8 o'clock. You see what I mean? In fact, I prefer to be on Zoom with them at 7:45. You know, a lot of students try to add the class. You see what I mean? Okay, so help me to help you. And of course, you don't want to do things last minute. It adds a lot of unnecessary pressure psychologically. Okay, yeah. I hope that's it for this semester. Then see you Monday during my office hour, and the Monday after that, or any time in between.
Okay. Thank you, Thomas.
You are very welcome. Bye bye.
Thank you.
Welcome. Bye bye.